In today's video, we shall take a closer look at moment of inertia. Moment of inertia is characteristic of a rotational motion. Basically, moment of inertia is what mass is for translational motion or a linear motion. We know from our previous video, if you have, let's say, a couple of masses, say one is 10 kg and the other one is 100 kg. It would be easier to move the 10 kg object compared to the 100 kg object, say from rest. So this is easy and this is more difficult. Likewise, if these two objects are moving, say with some speed, say 5 meters per second, just as an example, it would be easier to stop the 10 kg object, which is moving at the speed of, say, 5 meters per second, compared to a 100 kg object that is moving at the same speed. And this is because the 10 kg object has less inertia effect compared to the 100 kg object. The same thing happens in rotation. Let's assume you have a couple of disks that is spinning, like that. And the axis of spin is in the middle and coming out of the board. Let's say the spin is counterclockwise. Assume that the moment of inertia of that first disk is 20 in SI units, and the second one is 200 in SI units. Let's assume they are spinning at the same rate, namely the angular speed is 5 radian per second and 5 radian per second respectively. It would be easier to stop this disk from spinning compared to that disk, and the reason is the moment of inertia of the first disk is only 20 in SI units compared to the second one, which is 200 in SI units. It is important to note that in making such a comparison, the axis of rotations of these two objects must be of the same nature. What we mean is the axis of these two disks must be going through the center and coming out of the plane for both the disks. So clearly we see that the moment of inertia and mass, they have an analogous role, one for the rotational motion and the other one is for the linear motion. Here are the differences. Mass is fixed, doesn't matter what, and it's measured in the units of kg. Mass represents the amount of matter in an object. On the other hand, moment of inertia, which has a unit of kg meter squared, is not fixed. It depends on two things. The first is the mass distribution of that system, or the object. The second is the axis of rotation itself, namely the position of the axis of rotation. However, just like mass, moment of inertia is a scalar. So what do we mean when we say the moment of inertia is dependent on these two factors? To understand this, let's look at the most basic system. A system that consists of just a single object, and it is, say, rotating about that axis. So in doing so, it is executing a circular trajectory like that. Let's assume the mass of this object is m, and the distance, the perpendicular distance from the axis of rotation, is r. In this case, the moment of inertia of this system is m times the square of that distance. Now you can clearly see by changing the value of r, namely the distance between the mass and the axis of rotation, the moment of inertia of that same system can be changed accordingly. Now let's assume that you have a system that consists of two objects. One object has a mass of 2 kg and the right object has a mass of 4 kg, and they are connected by a massless rod or a string like that. Let's assume this object or this system is rotating about an axis that's going through the middle, like that. The distance of the 2 kg object from the axis of rotation is, let's say, r1, and the distance of the 4 kg object from the axis of rotation is, say, r2. So the moment of inertia about this axis of that system is quite simply 2 times r1 squared plus 4 times r2 squared. As simple as that. If you assume r1 is 1 meter and r2 is 2 meters, then the numerical answer for the moment of inertia of that system about that axis is 2 times 1 squared plus 4 times 2 squared, which will give you 18 kg meter squared. Now let's try to change the axis of rotation for the same system. We will try to make the system to spin about an axis passing through the 2 kg object like that. So the other 4 kg object will spin like that, for example, in a circular trajectory. So the new moment of inertia of the system about that axis, let's call it I prime, equals to that 2 kg times the distance between the 2 kg and the axis of rotation, which in this case is 0 squared, plus the other contribution comes from the 4 kg object, 4 times now the new distance between that 4 kg object and the new axis of rotation is 3 meters, so 3 squared. And that's going to be 36 kg meter squared. Now let's change the axis of rotation here, passing through the 4 kg object. What is the moment of inertia of the system about that axis? Let's call that I double prime. So the first contribution comes from 2 kg object. The entire distance from the axis of rotation is 3, so 3 squared, plus the second contribution is the 4 kg object. However, it is exactly situated on the axis of rotation, so the distance is 0, and square that, and you get 18 kg meter squared. Likewise, if you place the axis of rotation at any point in between the two masses, the values of moment of inertia in general would change as well. Let's look at the two values that we have at the moment. Let's compare the moment of inertia I in the first case and the second case. The first one is 18 kg meters squared, the second was 36 kg meters squared. That means it would be harder to accomplish the second rotation as compared to the first rotation. What we are saying is it would be easier to spin the system or rotate the system about an axis like that compared to an axis going through, say, the 2 kg object. What we have shown so far is the calculation of moment of inertia for point objects, namely an object occupying a specific point in space. What about if you have solid bodies? We shall just give the results here. If you have, let's say, a solid sphere, the moment of inertia of this solid sphere, let's say with mass m and a radius r, about an axis passing through the middle of that solid sphere, is 2 over 5 times that mass times the square of the radius. Say you have a solid cylinder instead, like that, and the axis is going through like that, and you want to rotate or spin the cylinder about the axis like that. So in this case, if the mass of the cylinder is m and the radius of the cylinder is r, the moment of inertia for such a cylinder about that axis is half times mass times r squared. Now we are talking about a solid cylinder. What about a uniform rod with mass m and length L? Let's assume you want to rotate this rod about an axis passing through the middle of that rod like that. So for such a uniform rod, the moment of inertia about that axis is 1 over 12 times mass times the square of the length. These results can be accomplished using a method of calculus, so we won't get into that in this video. The point we are trying to make is that the moment of inertia of a system is dependent on two things. One is the position of the axis of rotation and also the mass distributions of that system. Let's look at the following problem. For the system shown below, calculate the moment of inertia about an axis through A and perpendicular to the plane. So the axis is coming towards you and passing through that 0.4 kg object. So let's do that first. Moment of inertia through an axis passing through point A. Let's do one by one. Let's start with the 0.4 kg object. So 0.4 times the square of the distance to the axis of rotation. The distance is 0, so 0 squared, no contribution there. Let's get to the second object, 0.3 kg object. The perpendicular distance to the axis of rotation is 0.4, so 0.4 squared. And now the final contribution, the 0.2 kg object, that is that one. The perpendicular distance is that distance. Since this is a right angle triangle, we can use the Pythagoras theorem to determine the distance between A and B, and that's going to be 0.5 meter. So the contribution from that 0.2 kg mass for the moment of inertia, IA, is 0.2 times 0.5 squared. This is the perpendicular distance from 0.2 kg object to that axis of rotation. And the answer turns out to be 0.098 kg meter squared. Now let's do part B, the moment of inertia of the system about an axis coinciding with BC. So the axis of rotation is that line. As you can see, only 0.4 kg object will execute such a rotation in a circular manner, in a circular trajectory. So let's do the calculation. The first contribution is 0.4 kg. The perpendicular distance from such an axis is 0.4 meter, so square that. The second contribution is 0.3 kg, but it lies exactly on the axis, so 0 distance from the axis. Likewise, the third contribution, 0.2, the distance is 0 because 0.2 kg lies also exactly on the axis, so 0 squared. And you're going to get 0.064 kg meter squared. So this is the answer for part B, as opposed to 0.098 for part A. So what this calculation shows is that it would be easier to accomplish that rotation compared to that rotation, because the moment of inertia for the second case is smaller than the moment of inertia for part A, and that solves the problem. As always, thank you for watching.